talk in our session will be given by Julien. He's going to tell us about tools for quantum communication, improving photon correlations in polarization and orbital angular momentum. Julien.
Thank you. So our lab works on quantum communication. One example of quantum communication is quantum cryptography. And so essentially the idea behind quantum cryptography is we want to make more secure cryptography systems. Traditional cryptography relies on the fact that it's really hard to vector large numbers. But if you had a quantum computer, you could do that really quickly. And so quantum cryptography is an alternate method that is provably secure by relying on quantum superpositions. So the usual scheme is that the person who wants to send a message generates a pair of correlated photons, keeps one and sends the other one to the sender, to the receiver of the message, and encodes the message, and then they do these measurements together. But there are extensions to this using properties such as entanglement, using other variables, usually it's photon polarization, you can use other variables like momentum, angular momentum, and also adding antecedents. So our lab, my thesis was looking at two different ways to improve our quantum communication experiments. The first one I looked at was we do a protocol using entanglement and polarization states. So increasing the entanglement of the state we use would make us have better experiments. And another one I looked at was using orbital angular momentum as a photon variable. So here's a quick explanation of how quantum entanglement works. Essentially the idea, here we have photon polarization states. H represents horizontal polarization, and V represents vertical polarization, and then you can change bases into plus 45 and minus 45. So if you have this quantum state where you have 50% chance of measuring two horizontally polarized photons, 50% chance of measuring two vertically polarized photons, when you change them to a plus minus 45 basis, you still have complete correlation where both photons still have the same polarization. While if you start out with the classically correlated state, where you have 50% of the photons happen to be both horizontally polarized and 50% of the photons happen to be both vertically polarized, when you change the basis, you get 25% chance of getting each combination. So essentially what entanglement is in this case is when you change the basis, you still get correlations in the polarization states. So we produce entangled photon states by using spontaneous parametric down conversion, which is a nonlinear optical process that happens in a very Boy crystal, where you put in one pump photon and it splits into two photons that have twice the wavelength and half the frequency. And so since the two photons are correlated, you produce them at the same time, you have to conserve energy, momentum, angular momentum, and so those variables are correlated. And it's a coherent process which makes them entangled with those variables. And then for polarization, the specifics of the process means that we use type 1 spontaneous parametric down conversion, which means you're turning vertically polarized photons into two horizontally polarized photons and vice versa. And this actually happens only along the optical axis of the nonlinear crystal. So we use two crystals at 90 degrees with each other to down convert both polarizations. And so that means that the two polarizations don't have the exact same path to the crystal. And so then they don't accumulate the same optical phase through the crystal. And that means there's a phase shift between the horizontally and vertically polarized photons. So there's a phase shift. But it turns out that this phase shift is also wavelength dependent, since the index of refraction depends on the wavelength. And so since the laser we use has a bandwidth, so this is our spectrum of our laser, this goes from 402.4 millimeters to 403.4 millimeters. So mainly it's within, it has like a 1 nanometer bandwidth. And so that means that there's a spread in the phase shift between the horizontally and vertically polarized photons. And this spread results in less entanglement because there's a greater uncertainty of what the actual state is. So it means they can't be as volatile. So this is the setup we use to measure polarization correlations. So we have optics to prepare the right state, and then a down conversion crystal makes two signals, and then here we use a polarizer and the combination pathway with the polarizing beam splitter to measure the two polarization states. And so in order to correct the wavelength dependence of the spread, we add a pre-condensation crystal here, right between the quartz and the BDO, in order to add an opposite wavelength dependence phase. And so pretty much this group, one of their previous students in the group worked on this 2 years ago for his senior thesis. And we bought the crystal, he recommended it, it turned out it didn't work. So this summer I looked at this and did the calculation again and compared with what other groups have done and found that he was missing a factor of 2. So once I did that, we actually got a crystal that was 5.68 millimeters of quartz to cancel out the wavelength dependence phase to linear order. And so here's some data to show what that improved. This is before we put in the pre-condensation crystal. So the blue line shows the correlations in the horizontally and vertically polarized photons. So we expect these correlations to be very good because that's where we're producing our state correlated to those photons, our state correlated to those polarizations. But then when we switch the basis, the entanglement, the correlation in that basis will tell us how much entanglement we have. And we see here, the 45 minus 45 counts are pretty far from zero. There's a 0.12 ratio of the minimum to the maximum here. So that means we're not completely correlated. And after I put in the pre-compensation crystal, you see here it goes a lot closer to zero, and the ratio of the minimum to the maximum is now 0.02. So that's a way better correlation, a way better entanglement, and the measure we use is called the concurrence. It went from 78% to 96%, and that means we really have a very good state to do on our communication experience. So the other thing I looked at was photon angular momentum. This has been kind of a long-running project. Essentially, photon angular momentum is a state where the electric field intensity rotates along the beam path. And so this can be thought of as the plane of constant phase. So the wave front of the light beam is helical. So in the plane wave, the plane front is just a plane that moves forward. Here it's a helix that's spinning around. And when you time average it, you get this doing it. And the angular momentum of these beams is quantized by LH bar. So L is just a prime number. It can be any integer. And so the fact that it's any integer means that we have an infinite number of quantum states, which means instead of polarization, we just have the horizontal, vertical polarization. So it's a two-dimensional system. You can have a qubit of information. Here you can have a higher dimensional bit. And so that means you can do more different kinds of quantum communication experience. And so we measure the OAM by using holograms that shift the OAM by plus or minus 1. So here you put in a L equals 0 beam, and most of it gets sent to the first effector, to Blaze holograms, so it turns into L equals 1. And essentially you combine that with single mode fiber couplers that measure only L equals 0. And so in that combination, you can measure any of L equals -1, 0, 1. So that gives us 3 states to measure. And this is the setup. So it used to go straight this way when we're measuring polarization, but now we deviated to put it into these single mode fiber couplers. And so a few summers ago, Kelfer and I tried to align this the first time, and we produced these plots where one, so if it's on the fork of the hologram, it's a hologram pattern. So on the fork, it's measuring L equals 0. If it's off, it's measuring L equals 1. If it's off and measuring L equals 0. If it's on the fork, it's measuring L equals 1. So we'd fix one and then move the other one to see how the correlations change. And so here we expect a lot of L equals 0, 0 pairs, and not a lot of L equals 1, 0 pairs, because spontaneous parametric down conversion conserves angular momentum, so we expect the total angular momentum to add up to 0. And so we have this dip here and this peak here. So that's good, it's correlations, they're good. But however, the 1, 0 pairs here are not as low as we want them. They're like about 70 per 10 seconds. So we want to really reduce that and get better data. So we looked at previous members of the group and I. In previous years, we looked at reasons for why this was working. And so we found 2 big reasons. One of them is that since our holographic patterns are diffraction patterns and they have like curved lines, as you move across the hologram, the slope of the line changes, and so the first diffracted order moves a little bit. And so that means that if we align it well when we're at one position on the hologram, when we move the hologram so that it's producing the L equals 1 mode, the mode moves. And so that means we're not really rejecting the L equals 1 mode as much as we want. And the other problem is that the down conversion process produces a cone of light that's pretty divergent. And so we're trying to couple this into single mode fibers with aspheric lenses, which does help somewhat, but it doesn't really collimate the beam as much as it would. So we're having problems matching the mode of the down converted light to the single mode fibers, and so it doesn't reject the L equals 1 as much as we want. So I worked a little bit on these 2. First thing I worked on the alignment, but this didn't really work so well. As you can tell from this plot, this is where we'd expect the -1 coincidence to be, and there's definitely no peak here until the peak over here. So this was pretty much, I tried to align the beam better when it was on the fork. And so this was pretty much aligning to a minimum, which is very difficult. So we concluded from this that the strategy wasn't going to work, and we really need to address the mode matching issue first. So these are plots of when I tried to address the mode matching by changing the distance between the fiber and the coupling length. So by focusing the beam better on the fiber. And if you compare these to the previous graphs, the main difference is that I'm pretty much getting twice as many counts per second. So I aligned it a lot better this time around because we did it better, and also the ratios here are actually improved. The L equals 1, 0 are lower compared to L equals 1. but we're still getting non-zero here. But actually, this is, if you think about it, this is actually pretty good, because the ratio of 0, 0 to 1, 0 is 8 to, about 800 to 100, so 8 to 10, 8 to 1, sorry. And so if it were totally uncorrelated, then you'd expect to have, if the probability, so if you just decompose into the probability of getting 0 and the probability of getting 1, then we'd expect for 800, 0, 0, 100, 1, 0, then you'd expect 1, 1 to be down to like 64. But we're really getting more than 250. So there's definitely a correlation present. And so that's good. And so that means that in the future, we are going to better mode match and try to way to really collimate the down-converted beam using the optic system in order to really get better correlations. Okay, thank you.
Questions?
So can you describe how you, what kind of optics you might use to improve the mode matching?
So the beam is pretty divergent and gets pretty large, so we want to focus the beam and collimate it more. So right now there's just one lens between the hologram and the fiber. So that's just one focusing lens. So if we want to make the beam smaller, we use more lenses. We'd have to look more at what the actual characteristics of the down are to decide what kind of lens.
Could you describe, I'm sorry if I missed it, but I don't think I did. Could you describe the mathematical formalism that's used to describe that donut hole and it's now the transverse distribution of power?
Yeah, so it's the Laguerre-Gauss beam. So it's a solution for the transverse point pattern cylindrical pattern. And so essentially the solution has an e to the I of phi term, where that describes the wrapping of the face front. And so the now term is essentially controls how much OM has in the direction which is true, whether it's positive.
And the role of the hologram or the holographic gradient, I guess?
Yeah, so essentially that's just, the holographic pattern is just an interference pattern between the Gauss, the plane wave and the Laguerre-Gauss beam. So then if you put in Gaussian beam, then it turns into, Sean will discuss it a little bit more.
Other questions? Speaker again.
Oh, it shows the right away.
So the goal of mine is to computationally calculate the